So, you're interested in making a Game Boy emulator, right? But you're not sure how to start? In this video, I'm going to help you figure that out. It's not a step-by-step guide, but I hope it will help you get started and give you enough information to get going. I'm going to assume you know how to program, and you should be able to set up a development environment for a new project, whatever that means for your language of choice. You'll probably also want a version control system like Git. I'm also going to assume you don't know anything about the inner workings of a Game Boy, but you have played a Game Boy game before, either on hardware or an emulator, so you have some idea of how a Game Boy behaves. You'll also need some basic computery knowledge, like what hexadecimal numbers are, what a byte and binary are, and at least a very high-level idea of how a computer works. Something like that a computer has a CPU that gets instructions from memory, and reads and writes data from memory, and there's input and output. I'm hopefully going to have chapter markers so that you can skip things if you already know them. If you're not sure if you're ready to make a Game Boy emulator, have a look at my other video about that very question. I was actually reluctant to make this video. You see, I'm not making a Game Boy emulator, and I've never made a Game Boy emulator. I just wanted to draw some attention to a fun project. I've also been a professional programmer of computers for a while and an amateur Game Boy tinkerer for a bit, so hopefully I have something useful to say. I also don't want to give you detailed step-by-step instructions to build a Game Boy emulator, because, for one thing, like I said, I don't know what I'm talking about. More importantly, though, I think that figuring out all the things is part of the fun. I wouldn't want to rob you of that. So, if I say something incorrect or misleading, it was totally intentional and not a mistake on my part. If you want to make a Game Boy emulator with zero help, then you should probably leave now. Don't stop the video though, let it keep playing to help my retention stats. In fact, you should turn autoplay on and let it run for a few hours, or queue up a bunch of my other videos and let them autoplay to make it look like this video is really good for general YouTube retention. I hear that's an important stat for the algorithm. Oh, and remember to like and subscribe, and support me on Ko-fi, and leave a comment, and tell a friend. To make sure we're all on the same page, I want to talk about what exactly we're trying to build here. What is an emulator? An emulator is a computery thing that pretends to be a different computery thing. I'm saying computery thing because what counts as an emulator can be pretty broad and kind of vague. Strictly speaking, all those FPGA-based reproduction consoles like the Analog Pocket and the FPGBC could be considered emulators. We just tend to consider them differently, partially because of marketing and partially because they do provide some benefits over the software-based retro devices. So, we want to write some software, a program that pretends to be a Game Boy. The goal is to give it a game's ROM file and do some button presses and have the graphics and sounds it generates be as close as possible to the graphics and sounds a real Game Boy would produce. Broadly speaking, there's a spectrum of how you can achieve this. On one extreme, you could write code that simulates all the circuitry and transistors and such that are in the Game Boy. In a sense, that's what FPGA repro consoles do, and why they're often considered more accurate. On the other extreme, you completely ignore how the Game Boy works and just focus on getting the right behavior. You could imagine a neural network that's been trained so that you can input a game ROM and button presses, and it'll infer the graphics and sounds that should be produced. That would be pretty neat. We're not doing that though. We'll do something in between. But we need some details about the Game Boy. When Nintendo first made the Game Boy, they probably wrote a detailed description of how it should behave. This is a specification, or spec. Then, they designed and built the actual Game Boy hardware. Since the Game Boy was built in the real world and not some magical world where everything is perfect, the actual Game Boy's behavior is a bit different from what the spec describes. It has bugs. If we had the original spec, we could build a better Game Boy. It would only be better in a pedantic, useless way that nobody cares about, though. The spec doesn't matter anymore. What matters is the Game Boy. It's what's called the reference implementation. However it behaves is exactly how a Game Boy is supposed to behave. No more, no less. Even if some of those behaviors are bugs. Lucky for us, some hardworking folks on the internet have endeavored to document in detail exactly what the behavior is and have made that information free and available to everyone as a website called the Pandocs. There's also GameBoy, the complete reference, that goes into even more detail, and you can find many more resources on gbdev.io. The open web is a wonderful thing. The Pandocs will be the spec that we'll use to tell us what our emulator is supposed to do, and we get to figure out how our emulator is going to do it. I've been saying we and us a lot, but really, I mean you. You're going to be doing all the work, not me. I get to feel smug telling you what to do, like I know anything. It just felt more polite to say we. Now that we've got that settled, I'll continue smugly telling you what to do like I know anything. The core loop of what we'll be doing is we pick a part of the GameBoy to implement, read the Pandocs or other documentation to figure out how it works, try to build it, repeat. Really, it might look more like read the docs, try to implement, get confused, go back to the docs, get confused, stare at docs, stare at code, get frustrated, take a break, get a flash of insight while doing something completely different, go back to code, make progress, repeat. The amount of confusion and frustration may vary. So let's start. The GameBoy does three main things. It executes machine code, it renders graphics on the display, and it makes bleeps and bloops and shh sounds. Let's start with executing code. This is an arbitrary choice. Start where you want. GameBoy machine code is made up of instructions. What instructions? These instructions. It is extremely not obvious what this table means. We'll get there though. For now, it's probably better to look at the instructions like this. This is from the RGBDS documentation. Strictly speaking, it's assembly code, which is meant to be human readable. When you program in assembly code, it looks like this. So readable. RGBDS is an assembly language toolchain for the Game Boy and Game Boy Color. That's why it has this documentation. For now, I'll be talking about assembly code instead of machine code, since it's easier. Otherwise, I'd just be showing you a bunch of numbers instead of text. I'll let you know when I switch back to machine code. In this documentation, there are 107 instructions, and we'll have to implement all of them. That sounds hard, but I'm not worried, and not just because I'm not the one doing the work. It's because most of them are just variations on the same basic operations. For example, there are 22 load instructions, and they all do basically the same thing. They copy data from one place to another place. The place can be either a register, memory, or a value written into the code. A value written into the code is called an immediate value. When an assembly instruction is accessing memory, it uses square brackets. The thing in the square brackets is interpreted as a memory address. It can either be an immediate value or a register. A register is a small bit of memory that lives inside a CPU. It's only big enough to hold a single value. The CPU uses registers to do operations faster without having to go to memory for everything. Usually what happens in assembly code, very broadly speaking, is you load some values, from memory or immediate values, into registers, do some operations on that data, then store the result back to memory. The Game Boy has 7 general-purpose 8-bit registers. Some of these registers can be combined into 16-bit registers, like this. The A register and the HL register are special. The A register is called the accumulator. All binary operations have the form A equals A op thing, so it's like A is accumulating the results. The A register is also the only register that can be used for certain load instructions. The HL register is usually the only register that can be used for addresses when accessing memory. The only exceptions are simple load instructions. There are some special load instructions I'd like to mention too. The first are the increment and decrement loads. They're for loading and storing sequential values from memory. They use the HL and A registers. They're either written as LDI and LDD, or the I and D are put with HL as HLI or HLD. The other special instructions are the LDH loads. These loads from high RAM. These are faster than regular loads, but they can only access addresses between FF00 and FFFF. You can either specify the address as an 8-bit immediate or with the C register. The Game Boy also has 3 special purpose registers: SP, PC, and F. SP is the stack pointer. It's the address of the next spot in the call stack. It's set to FFFE when the Game Boy starts. And just so you know, when the stack grows, SP gets smaller. This will either make perfect sense to you or seem totally backwards. PC is the program counter. It's the address of the next instruction to execute. Every instruction changes PC, either by incrementing it by the number of bytes used to encode the instruction, or by setting it to a particular value. The last special register is F, which is the flags register. It's even more special than the other 2 special purpose registers. I don't really feel like explaining it, so I'm going to let you figure it out. You can find more information about it on the Pandocs under CPU registers and flags. Phew! That was a lot of information, but I think you know enough about Game Boy assembly code to get you started. If you want to know more, I'd recommend trying to write some. There are a bunch of tutorials to help you get started, and it'll probably help you build your emulator. If anything I said was confusing, please ask for clarification in the comments. Alright, back to machine code. I said before that assembly code was more readable than machine code. That's because machine code looks like this. This is what your emulator is going to have to interpret. The first thing I want you to notice is that the instructions aren't all the same length. You won't be able to just slice up a ROM file into equal-sized chunks and treat it like an array of instructions. I mean, there's other reasons you can't do that, but this is also a reason. You have to use the first byte to know how many bytes are part of the instruction. That first byte tells you what the instruction is, mostly. And that's where this table comes in. It organizes the instructions by their first byte. An instructions row tells you the first 4 bits of its first byte, and the column tells you the last 4 bits. Finding an instruction on this table tells you its first byte, and knowing an instruction's first byte lets you figure out what instruction it is. Except, this isn't all the instructions. That's where byte CB comes in. It's the prefix byte. If an instruction starts with CB, it means you have to look at the second byte to know what the instruction is. You can use this second table for that. If an instruction has an immediate value, then it'll also have an extra byte for 8-bit values and 2 bytes for 16-bit values. Be careful though, the Game Boy is little endian, which means the first byte of a 16-bit value is the least significant byte of the value, and the second byte is the most significant. This is only confusing because we tend to write byte data left to right, but numbers right to left, or something like that. I really hope I'm saying that right. Now that I've explained Game Boy machine code perfectly and you all understand it and I totally didn't confuse you, you have enough to start building something. You actually have some options depending on how small you want your first steps to be. If you want to really focus in and do something small, you can start by writing code to decode individual instructions. Maybe something that, given a byte, it tells you the corresponding instruction and how many bytes are left. Or, given an array of bytes, it decodes the first instruction. This kind of start will let you start getting comfortable with the project and also gives you an early win. The risk with starting here, though, without broader context, you may end up writing code that doesn't fit into the design you end up with later, and you'll have to throw out some code. It won't be a waste, though, because it will get you started and help you learn and help you start to figure out that final design. If you want to get a bit more complicated, you can hard code some machine code as a byte array and start writing the code that can handle multiple instructions. Or you could get your machine code from the same place a Game Boy does, a game's ROM or read-only memory. For an emulator, that means a ROM file. You can get a ROM file either by programming and building one yourself or by ripping one from a physical cartridge. Those are the only 2 possible ways of getting a ROM file. A ROM file is just an ordinary file on your computer, but it's important that your emulator code reads it as a binary file. How to do that depends on the programming language. A number of languages pass the value RB for read binary to the open file function. Hopefully you can figure it out, or you have somebody to ask if you don't already know. If you're stuck, you can ask in the comments. Be sure to say what language you're using. I'll try to make sure to answer, or maybe someone else will. But know this, I will delete any comment that makes fun of someone asking about this, or anything else that you might think is obvious or too basic. And you better not be criticizing people's language choice either. Anyway, once you have the file open for binary reading, go ahead and read it into a byte array or uint8 array or whatever your language uses. You want to make sure you can index to individual bytes though. The Game Boy operates primarily on 8-bit values, so we need them bytes. If your language of choice doesn't have a way to do that, you're going to have a harder time. You'll have to write some code that gets around that. Or switch languages. If you're in this situation, please leave a comment telling me what language you're using. I'd be very curious to know about it. Now that you have the ROM data, you can start decoding it. But where do you start? At index 0100, of course. That's where the Game Boy starts executing a game's code. How did I know that? I don't remember. I think I learned it when I was learning to write Game Boy assembly code. If you did the cartridge header decoding test project I described in my last video, then you would have read the cartridge header page from the Pandocs, and you hopefully would have noticed the first part of the header is the entry point starting at 0100. Or you could have read the page about the power-up sequence that mentions it as though it's something you would already know. It's information that's kind of sprinkled around various Game Boy dev docs. I'm really not sure the most obvious way someone would learn this though. If you have any ideas, please let me know. So execution starts at ROM address 0100. And since I had you load the ROM file into a byte array, address 0100 corresponds to the array index 0100. Easy peasy. If you watched my first video about Game Boy emulators, you might remember that I suggested writing code to convert a ROM file back into assembly code. A good place to start, if you do plan on building a full emulator, would be a tool to disassemble a Game Boy ROM to turn it from binary machine code back into somewhat readable assembly code. This is called disassembling. You may be surprised to find out that I did not think that idea completely through. It's still an interesting idea, but it may be much harder than I made it out to be. In the normal case, and probably most real-world cases, it's not so bad. In the general case, it's provably impossible. So it really depends on how deep you want to go. If you're interested, you might find terms like static analysis and abstract interpretation useful. So yeah, now you can load a ROM file, so you can start decoding and executing instructions. You could use RGBDS to create super simple ROMs to give you something to test on. If you're feeling particularly responsible, you could even start building a suite of automated tests. Maybe do some test-driven development. That might be smart. You could also load up Tetris and see how far you can get. Really, that could be what drives you for a while, trying to get Tetris to run. There's a lot to learn and figure out still. In some ways, executing machine code is the simplest part of the emulator. I'm going to be making at least one more video to help out with the other parts of the emulator, so be on the watch for that. This video is hopefully going to help you eventually get to a point where you have a way of keeping track of all the registers with PC initialized to 0100. You'll load in a ROM file, then enter an infinite loop. In the infinite loop, you'll use PC to index into memory to get the next instruction, using the first byte at PC to figure out how to decode the instructions. You then execute the instruction by updating stuff like the registers, and you update PC either by moving it ahead to the next instruction or setting it to a particular value. Then repeat. Assuming you don't get stuck and give up before you get to that point. Anyway, good luck, bye!